motion up to the basic kinematics and dynamics of SHM both, and we have seen the example of the horizontal spring mass system. So we will continue today with more examples of spring mass systems, including vertical spring mass system, and then move on to pendulums to complete simple harmonic motion. So anyhow, let's begin. So just to quickly recap everything we have understood, general equation of SHM we have seen is that the displacement from the mean position is given by an equation like this. Okay. In this equation, as you know, A is called the amplitude, omega is the angular frequency, this is how it is related to frequency or time period. Phi is called the initial phase or phase constant. And this implies that the instantaneous velocity as a function of time becomes E omega cos omega t plus phi, and the instantaneous acceleration becomes minus A omega square sine omega t plus phi. Okay. So this shows us that the maximum speed is A omega. This shows us that the maximum acceleration is A omega square in magnitude. Now also, this is the dynamical condition. Net force is of the type minus kx. So just go through this section once and let me know in case of any doubt. We'll discuss with a couple of examples. Okay, so just try out this question. We'll discuss. So just go through this section above and try out this question. The concepts you require to solve this question are there above. Yes, very good, Varun. Your answers are correct. So let's check out the question. So it says amplitude is 2 centimeters and time period is 2 seconds. So implies that omega, which is 2 pi upon t, is equal to pi radians per second, and frequency, which is 1 upon t, is 0.5 hertz. Now, x in general is so at an instant when x is equal to plus 1 centimeters, sine omega t plus phi must be equal to plus half. So v is a omega cos omega t plus phi. So the speed must be a omega into mod of cos omega t plus phi. Now you can see from here that if sine theta is half, it means cos theta so therefore that implies that the speed at that instant is so much. Okay, so I have shown you with the proper steps over here. At the exam level, you can do this much faster by just understanding like this, that okay. Now about the acceleration. For the acceleration, use the relation that is this. Okay, so acceleration is minus pi square. So pi square is approximately 10. We can say, okay, the acceleration is approximately minus 10 centimeters per second square. And So the direction of the acceleration is towards the origin, as always the case, and the magnitude in this case is 10 centimeters per second square. So just make a quick note of this. We'll move on. Okay, now next thing about SHM, we'll quickly revise is that so at t equal to 0, the initial position you can see is given by A sin phi, and the initial velocity so from these equations we can see that amplitude has this kind of relationship with initial position and velocity. This comes from the fact that sine square phi plus cos square phi is equal to u dt. So from the first equation, x naught by a whole square, and from the second equation, v naught by a omega whole square is equal to 1. So from this we get this relation. So anyway, the important thing is the exact relationship, and the other is that phi, the phase constant, is tan inverse of x naught by v naught into omega. These two are extremely important relations here. That is the amplitude and the phase constant phi in terms of the initial conditions. Amplitude and phi in terms of initial conditions x naught and v naught. So let's look at a quick example based on this. A particle in SHM has x equal to 6 centimeters at t equal to 0. Okay, so just try this out, people. Yes, Ruja, your answer is correct. Also, Varun. So the amplitude is 10 centimeters, and first of all, the information from this time period is 8 seconds, means omega is pi by 4 radians per second. Yeah, so x naught is 6 centimeters and v naught is 2 pi centimeters per second. It means that the amplitude is to be square root of 6 square plus the phase constant is tan inverse of x naught divided by v naught into omega. Phase constant is 37 degrees. So the equation of SHM from here becomes that x is equal to 10 sine pi by 4t plus 37 degrees, where x is in centimeters, t is in seconds, and v max is a omega. So 10 into pi by 4 or 5 pi by 2 centimeters per second, and maximum acceleration is a omega square. So 10 centimeters into pi by 4 whole square. Okay, people, so hope this question is fully clear. Yeah, Varun, about major test tomorrow, just revise the previous lectures of SHM and today's lecture. Spring mass systems, kinematics of SHM, these kind of things. Questions we are doing in class today are sort of revision also. Okay. Apart from what we have seen before, we will just learn a couple of new things today, which is combination of springs and vertical spring mass system. So just adding that to what we have learned previously in SHM, that is the portion for SHM in general and what is coming tomorrow's test also. So now let us come to spring mass systems. So what we had learned previously is that the most basic example of spring mass system, if you have a single block attached with a single spring on a horizontal frictionless surface, then it performs SHM. Okay. This is a smooth surface. So now, for example, if it is given that the spring constant is 25 newtons per centimeter and the mass of the block is, let's say, 4 kilograms. Okay. And initially the block is at equilibrium at rest. Okay. And at t equal to 0, an impulse like this, an impulse equal to is applied. Okay. So find the time period of its SHM. Okay. Then find the amplitude and the phase constant. From that, write the equation of SHM. You can find various other things like maximum speed of the block, maximum acceleration. So these are all additional things that we can directly find out from formula. The main thing is finding out the time period, amplitude and phase constant. So the background here is that we had seen that if you have a horizontal spring mass system like this, when it is at natural length, the acceleration is 0. So this is your mean position. But from this, when we take it to a positive displacement, the tension in the spring creates a negative acceleration. Or when we take it to a negative displacement, now the tension like this again creates an acceleration. It's opposite to displacement. So d2x by dt square is minus k by mx. So omega square is k by m. So this concept we have to apply over here. So the moment we know that this is the case, we know that x will be of the type a sine omega t plus phi, where omega is square root of k by m. Amplitude comes from initial conditions, and so does phase constant, kind of thing. Okay. So just these simple ideas have to be applied to the numerical problem here. Rest of it is direct. Just try it out. We'll discuss. Yes, very good. That's correct, Aruja. So we will directly apply the formula here. Okay, for spring mass system, omega square is k by m. Only thing is make sure to convert to SI units. Okay. So omega is t by 2 or 25 radians per second. So time period will be approximately 0.25 seconds. We have converted the units. Varun, as you can see, we have converted the units. Okay, now you can see that when we apply this impulse at t equal to 0, this will result in the block starting to move like this with a velocity, whereas this is at natural length. So our x naught will be 0. So our v naught with proper sign convention will become minus j by n. So that is so initial velocity is minus 3 centimeters per second. The minus sign is only for the direction. The important thing is this. Okay. Whereas our omega was 25 radians per second. Because it's starting from the mean position. It's given to you that it starts from equilibrium. The block was initially at equilibrium. It's given to you. So now from these two, we can see that the amplitude converted to 1.2 millimeters also. The amplitude. Okay. Now the phase constant. Now notice that here x naught is 0 and v naught is negative. So that means a sin phi is 0, a omega cos phi is negative. That means sin phi is 0, cos phi is negative. So phi should be pi. In general, tan inverse 0 can give you two solutions, 0 or pi. So here it will be this because of this reason. Okay. So our equation of SHM will become Okay, people, so hope this type of question is clear now. Okay. Now, next we will move on from this to something which has combination of springs. So first of all, let us see the related formulae for combination of springs. So this type of a combination, it is called a series combination. So what happens in this type of combination is that if you displace the block by some amount x, let's say, then individually the springs which were of natural length L1 and L2, they get stretched by x1 and x2 respectively. And they apply force like this. So we have x1 plus x2 is equal to x. So from this we understand that the net tension can be written as some equivalent spring constant into x, where that equivalent spring constant is given by this formula. So this becomes the most important. So at a problem solving level, what we do is we convert this to a single spring where K equivalent is the equivalent spring constant for the combination. So this first example, this is called a series combination. So in general, if we have more than two, we have n number of springs, then they are equivalent to a single spring, such that this is the general formula. Just make a quick note of this so that you remember this. You've seen this earlier in mechanics, okay, but it's used quite often in simple harmonic motion combination questions. Okay, now next, let's understand the parallel combination. Okay. So in parallel combination, one way of connecting it would be like this. So if we move the block by a distance x, both the springs are having the same amount of extension. So the net force acting on the block is like this. So that becomes equivalent spring constant into x. So in parallel combination, equivalent spring constant in general, whatever number of springs we have connected, it becomes like this. Now, one more sort of situation we should keep in mind for parallel combination is if we connect springs from either side. This is not a series combination. This is also a parallel combination. If this is of natural length L1 and natural length L2. Now here, if we displace the block by x, you'll see that one of the springs gets compressed while the other one gets extended. So this becomes L1 plus x. This becomes L1, L2 minus x or whatever. Okay. So both of them still apply the force in the same way. So still the net force is T1 plus T2. This is also a parallel combination. So let's also work out a quick example based on this. So typical kind of SHM example. So we have connected 3 springs to a block like this. So K1 is 6 newtons per centimeter. K2 is 3 newtons per centimeter. And K3 is 2 newtons per centimeter. And the mass of the block is 1 kg. Find the time period for SHM of the block. So this is another typical type of question at NEET level, or for that matter, even JEE Mains level. Okay. Of SHM of spring mass system where we have a combination of springs. So all these things are quite easy in this chapter, SHM, formula based type of things. Okay. The more tricky thing was kinematics of SHM, the relation between phase constant and amplitude with x naught, v naught, etc. The type of questions we were discussing earlier. Yes, very good, Rahul. That's correct. Okay. So we will see here that this is a series combination of springs. Okay. So it can be replaced with K is equal to K1, K2 divided by K1 plus K2. So that will become from here 2 newtons per centimeter. So first step, we can reduce this to this. Okay. Now next step, what we can do is you can see that this and this is a parallel combination. Okay. So this can be reduced to an equivalent spring where K equivalent is K plus K3. Okay, so it is, so the equivalent spring constant is 4 Newton per centimeter. Now, while calculating time period, you just have to be careful that you don't forget to remember omega square is equivalent spring constant divided by mass. So don't forget to convert the units. So 1 kg upon 4 into 10 raised power 2. So you're converting this to Newton per meter kgs. Okay. So it becomes 5 by 10 seconds. So Krupa, just that added point of conversion of the units, you have to be very careful because typically spring constant is always given in hybrid unit Newton per centimeter, which is neither SI nor CGS. Okay, so hope the concept in this question is clear to all of you. Just go through the combination once more. How I've reduced it from first 3 springs to 2 springs and then from 2 to 1. Okay, now let's move on from here to vertical spring mass systems. It's just very simple extension of spring mass systems that we've seen before. So we have a situation like this, that you suspended a block from a ceiling like this. Now initially, let us say this is in equilibrium position. So this is having some extension because there is gravity acting. So in equilibrium position, you can see that the free body diagram indicates that kx naught has to balance mg. So this is not the initial extension here. This is the equilibrium state. Of the block. Okay. So now what we'll do is show that if given vertical displacement, whether it's up or down, it doesn't matter, vertical, the block performs SHM, and we want to find the time period. So just note down this section, then we'll discuss more about it. Okay, now see, what we have to understand is that from this equilibrium state, so the other thing we have to understand is, since we are talking about vertical displacement, we will take a different variable. Okay. So when this is at the equilibrium state, the acceleration is 0. That we've already understood. Now from this equilibrium state, if we give it, so we will take this as our y equal to 0 position. Okay. And from here, if we give the block a downward displacement of y, okay, then we will see that the spring's extension now changes and it has an upward acceleration. So in the second case, x has become x naught plus y, where y is the downward displacement from mean position. A mean position is y equal to 0. So at this position, we can see that we got the free body diagram. Okay. Whereas the equilibrium state was that when we compare these two equations, we will get the equation of SHM. Okay, so this is how we calculate the time period or frequency of a vertical spring mass system and show the equation of SHM. So it's the same formula for frequency and time period. The only difference is that in this, what happens is the equilibrium position is not the natural length position of the spring. Okay, it is Okay, so ultimately spring mass systems are very easy. The formula for omega square in any spring mass system is K by M, whether it is horizontal or vertical. And if you have a combination of springs instead of a single spring, just replace the K with the equivalent spring constant that you can find from series and parallel combination concepts. Now, the only difference between horizontal spring mass system and vertical spring mass system is that in horizontal spring mass system, the equilibrium position is where the spring is at natural length. In vertical, at equilibrium, the spring is not at natural length, but the tension in the spring is balancing the weight. Rest everything else is the same. Okay. Now we move on to the last part of SHM, which is what we call angular harmonic motion of a pendulum. So any shaped pendulum, for example, if you have something like a rod which is hinged over here. Now, if it is given an angular displacement, it tends to go back and forth like this, the fixed time period. So from the vertical position, if the angular displacement is theta, then theta should be E sine omega t plus phi. That is the only difference in the equation, that theta is angular displacement. In radians, let's say, and E is angular amplitude. Again, in radians. Rest of the things are the same. So now we will see how to calculate the value of omega for a couple of different types of pendulums. So first we will see what is called the physical pendulum, or it is also called compound pendulum. So it performs angular harmonic motion for small amplitudes. Just make a note of this, then we'll discuss further. Okay, so a physical pendulum consists of basically any rigid body which has a hinge at the point P and center of mass at the point C. So it is hinged at the point P such that it can rotate about a horizontal axis through P perpendicular to the diagram's plane. Okay. So it can basically rotate like this about that hinge at P. And C is the center of mass. So when C is vertically below the point P, the net torque is zero. So we have equilibrium. Because it's an angular system, so instead of net force being zero, the condition for equilibrium is that net torque is zero. So just make a note of this section. Okay, so now what we can see is that if we give it an angular displacement from the equilibrium position, okay, where the center of mass has come here. So let's say this distance is d. So from the vertical position, we've given an angular displacement theta. Now you can see that mg acting through this creates a torque, which is like this. So there is a restorative torque. So we have the equation torque is equal to I alpha. So the torque will become mg into its moment arm, which is d sine theta. I'll just again show you how the moment arm is d sine theta. See, this is the axis at t, and this is the line of action of mg. So this distance here, this is the moment arm. And because this distance is d here, and this angle is theta, you can see the moment arm is equal to d sine theta. So torque becomes force into moment arm. So the torque becomes mg d sine theta. And the sense of the torque is like this, you can see. So this torque is equal to about the axis at t. So now alpha is minus d2 theta by dt square, because it is opposite to angular displacement theta. And sine theta can be approximated as theta for small angles. So therefore we have the equation that we have the angular harmonic equation. So omega here becomes square root of mgd divided by I. So this is the formula for time period of a physical pendulum. We'll just take another couple of minutes to finish this section so that SHM is done. Okay, so let's just see quick application of a couple of formulae here. So for example, if I have a physical pendulum that consists of a thin uniform rod, which is suspended at this end, P. So this is a thin uniform rod of mass m and length L. Now I want to find the time period for angular harmonic motion with small amplitude. The small amplitude is necessary because otherwise we don't get the equation of angular harmonic motion. So we know that omega is going to be square root of mgd divided by I, where d is the distance of the center of mass C from the axis, which is P. So in this case, the center of mass is at a distance L by 2. Okay. And I is the moment of inertia about the axis at T. So in this case, D is L by 2 and I will be ml square by 3. So this is the knowledge you need from rotational mechanics to substitute over here. So time period, which is 2 pi by omega, this here becomes the formula for time period. Another very simple example is the simple pendulum, which you can think of like this special case of physical pendulum, where you have a string, so massless string and a particle, mass m attached. So here you can see the point P is here and the center of mass is here. So the distance d is equal to L and the moment of inertia is ml square. So time period becomes the formula that you are used to from class 9, 10th level. This kind of formula is there. In the same case of the rod, suppose we had a situation where the rod is suspended at a point like this, which is at L by 4. Then as the rod would rotate, it would go like this. With respect to that point P. So here we would take D as L by 4 and we take I as ml square by 12 plus m into L by 4 whole square. That is ICM plus md square. So this would become and accordingly we'd substitute in the formula. So D would be L by 4 and I would be, that value would become, if you take 1 by 4 common, you have 1 by 3 plus 1 by 4. So 7 by 48 ml square. This would become my I. So accordingly, I would have to adjust the formula for time period. So you can see that the same rod suspended about a different point gives you the same different time period. Here I would give you a factor of 7/48 and D would give you a factor of 1/4. The time period would become 2 pi under root 7/12 L/G. Instead of 2/3 inside the square root, we have 7/12. So that is how you have to basically do the the variation problems. So the variation is basically about calculation of moment of inertia and the distance of the center of mass. So you can see this part of SHM is really very simple. It's formula based, whether you have spring mass system or physical pendulum. In spring mass systems, you have to just know the combination of spring formulae. And in physical pendulum, you have to just know how to calculate moment of inertia using rotational mechanics concepts of moment of inertia. And of course, center of mass, distance. The rest is formula based. The tricky questions of SHM, again, I'm repeating, are more about the kinematics of SHM type problems, which we were discussing earlier. Okay, so first of all, go through the problems we've done in the last couple of lectures, today's lecture and the last 2 lectures of SHM. Plus, I will send you a list of questions to do from the module, or I'll send you a sample assignment which you can work out. Okay, so that's it for today's session, people. We will pick up from the next lecture, doing more questions of SHM and then moving on to this thing, waves, which will be our next part of the syllabus. Okay.
Bye, so thank you.